you guys have the calculators, have them out, have them in front of you. We'll be changing students of whole limit, which is section 10.7. I don't think we actually need our calculators for conditioning the rest today. We have mostly next one. But if you do get to work on homework, then you might need it in part and extra. So one more thing to think about is for the quiz that's coming, let's see, 10.6. That's why I started talking about the calendar. Issue 10.6 today, 10.7 tomorrow, 10.7 on Wednesday. Probably quiz on Thursday. Maybe like a 20, 25 pointer. One page front and back, kind of like chapter 90. It's not a big, huge deal. There isn't tons to memorize. It's kind of more of an understanding. But like plugging into tables and being circle and stuff like that. So just keep in mind as you're doing homework, we're not having like a huge review day or anything like that. And time is kind of stressful. So hang in there. We're going to probably have a quiz on Thursday. I'll talk to Mr. Che. If for any reason we feel it's not fair or anything like that, maybe we'll have it on Friday, but right now the plan is on Thursday. Here we go. So, wasn't the first example of eliminating the parameter a lot easier than the second example? Yeah. First example, it was really easy. I'm just going to get my little pointer out. It was really easy, mathematically speaking, in order to hopefully solve for t in the x expression. Remember, that's step 1. Get t alone in terms of x, and then just go into the second equation. This is just substitution at its core. So only one variable, plug it into the second equation. Plug in, chug, simplify. Remember, eliminating the parameter, we're just trying to see the path. We're ignoring the timing because we're more used to functions in, or I should say equations in, function rectangular coordinates than in parametric. But then I gave you this one, kind of threw you for a loop, some of you. So let's walk through the process. I kind of solved it, and I didn't really talk about it. The bell rang, and you guys were all like, okay, who cares? It's Friday. So, step 1 was still the same. Step 1 was still take the x equation and solve for t. But some of you got stuck in that step because there was some algebra that was not quite basic, not quite elementary. Well, some people call it elementary. That's okay. So what I did, and some of you might have thought of it, might not have thought of it, I always like to look at an expression, and if I need to somehow break it apart, if I see division, I multiply. Just the algebra has been trained in me. I multiply. So I multiplied up the square root because I'm like, well, I don't like division. That makes everything harder. So I multiplied by the square root. I know that's backwards for some of you, but I multiplied by the square root. That's how I got this expression right here below, which is where I started solving. In order to solve for t, I needed to get rid of this x, so I divided it to the other side, as you guys can tell right here. So I divided both sides by x. This one canceled. This one remained. Then I had to get rid of the square root, which I did by squaring. I'm also going through because some of you guys didn't get it or didn't get it correctly or totally just said forget it. So I'm giving you time to get the example written down. As you square 1 over x, you get 1 over x squared. 1 squared is 1, x squared equals x squared. Last but not least, this little minus 1 came from getting rid of the 1 once the square root is gone. Now, once you solve for t, eliminating the parameter, substitution. Once you solve for a variable, usually you have to do what? Plug it in. And there's no exception in this case. So we solved in the x expression. We went to go plug it in. Looks like little snakes or something, and they're not showing up. There we go. We're going to go plug the t expression into the t's, and that's exactly what I did here. I plugged in that expression for the first t, that expression for the second t. There was another plus 1 as indicated in the equation above. I was able to see real fast that these two 1s cancel out, which was nice. But then I saw, as you guys hopefully have seen from me all year, I try to be as consistent as possible, that when I have a complex fraction and I have little denominators that I don't like, I tend to multiply top and bottom by that little denominator. I needed to distribute it into each of the pieces. X squared over x squared, you just get a 1. X squared times 1 with a minus, you just get minus x squared. In the denominator, the 1s are already gone, the negative 1 and the positive 1. So when you multiply 1 over x squared times x squared over 1, you just get a 1 remaining. I at which place we could say, hey, sweet. And even though these expressions, even though these equations in the very beginning looked very complicated, well, now that we see it in function mode or in rectangular coordinates, guys, isn't this just a parabola that's been shifted up 1 and flipped down? That's the path. Now the timing is complicated. Look at those equations up above. The parametric are pretty complicated, but it's just a downward facing parabola with an intercept of 0 and 1. So once again, there are definitely some nice things with parametric equations. Let's see if it'll come back to life. Some little things we take for granted. Parametric is nice in that you can see where something is going on its path of motion. You can figure out at different times where it is. It can be more realistic to life as far as not many things moved in this way forever downwards. Things move parabolically, but it's like from the ground to the ground, and it stops at some point. Parametric are nice, but they are complicated. It's a lot nicer, a lot easier if you can get them looking like little functions that we're used to. Guys, here's one more weird, quirky example. Remember I told you that the parameter in a parametric equation, it can be t, but it doesn't have to be t. Now sadly, I did go ahead, and not sadly, it just looks a little confusing. I did write this still as x of t and y of t because in your calculators, no matter what you do in parametric, let me go back, I was going to pull it. In parametric mode, when you go to type in, you can't type in betas. It is what it is. Your calculator's programs will only allow t's as the third parameter, but in the mathematical realm, you could have thetas as well. And they usually just use thetas when you have trig, like you're kind of used to. It is a third parameter. It's not necessarily talking about time, but it still could be, I suppose. But it is just a third variable. And so if we were to plug this into our calculator, we would go ahead and do 2 cosine of t, even though it says a beta, no big deal, whatever. It's a third variable. Just make it consistent. So then 3 sine of t. So we have 2 equations, both in terms of t, aka in terms of theta. It doesn't make a difference. It doesn't need to be super confusing. It's just a new variable. Just think we're using betas to make it nicer on your brain. Now, we could graph it and we could see what it is, but I actually want us to come back here and think first of all about the algebra. How do we eliminate the parameter? Now, I'm going to show you something a little crazy. It's actually kind of like calculus BC algebra used in trigonometry, used in calculus BC for some particularly confusing examples. However, let's use some AB. I will show you that we could take the x expression and solve for, well, okay, hold on, it's going to be a little different. We could take the x expression, let me go ahead and move this over here where I'm going to do it. There are 2 ways to solve this problem. Take the x equation, although now it's not in terms of t, it's in terms of theta. So we're going to solve for theta. Then we're going to plug in the theta expression to the y equation. And the third step, technically kind of understood in, I don't know, almost all math problems, is simplifying. That is a thing, and it is possible. I'm just trying to show you that you don't have to do it this way. You can, you just don't have to. And I'll show you the alternate way of solving. Let's just split the page in half, right? I'll show you the alternate way of solving in just a second. I think I can fit all of this. I move this down. Okay. Alright, so then we would take the x expression, we would solve for theta. To solve for theta, to get it by itself, I would do, let's see, x divided by 2, I suppose, equals cosine of theta. So that's like step 1. Solve for theta. Theta is equal to cosine inverse of x over 2. Remember, to undo cosine, cosine inverse. I'm going to go ahead and zoom in over here. I'm trying to still let you guys see the equations in the top left hand corner. Then, step number 2, we would take what theta equals, which we have right here. We would plug into theta into the y equation. We would have y is equal to 3 sine of cosine inverse of x over 2. Yeah, right? That's why. Now the crazy thing is with inverse, remember we actually are thinking of this as a ratio of sides. X over 2 is a ratio of sides. To be specific, it's adjacent over hypotenuse because it's cosine. And to be honest, sine is just looking for what's opposite over hypotenuse. Hold on. There's a difference. This one we know adjacent over hypotenuse. This one we're trying to find opposite over hypotenuse. Well, it sounds like there should be a triangle, but I don't see one. I'm just saying this is one option. This is not the way you have to go. You make one and you say, well, okay, great. There's this triangle for this dude named theta. And, as you can tell from the example above, this dude named theta has an adjacent and a hypotenuse of x over 2. And I don't like it because it's a variable. But all good math students would say, well, fill in that third side with Pythagorean theorem. And I don't like that there's an x there, but still we could say that the third side, which is a leg, would be the hypotenuse squared minus the leg squared. So the arrangement of the Pythagorean theorem. X squared plus unknown squared equals 4. So you do 4 minus leg squared and square root it. And the crazy thing is, if we're just trying to find opposite over hypotenuse for y, we could say y is equal to 3 times, well, look at your triangle now. Who's the opposite? Who's the adjacent? And you're right. Who's the opposite? There it is. Who's the, sorry, the adjacent, that hypotenuse. The opposite is square root of 4 minus x squared, because that's what we're trying to find. Look at the arrows. We're interpreting x over 2 is the adjacent over hypotenuse, but we're trying to find for this entire piece, we're trying to find the sine. We're trying to find the opposite over hypotenuse. So far, this is one way of solving. The theta's gone, you have y in terms of x. We plug that in your graphing calculator and function mode and see what it is. Here's for the alternative way of solving. Alternative way of solving uses, well, I'll say uses, what we know about trig properties. Some of you might be a little more scared of this one. However, this one is, in a way, a little bit nicer, but it's more out of the box because you're not taking the x expression and solving for theta. Because frankly, it's messy. Instead, you are going to solve x and y for not theta, but for the trig expressions. Solve x and y for the trig. So get the trig alone, get cosine alone, or get sine alone. Get tangent alone, or get secant alone. Get whatever you have alone. Number 2. The properties that we want to use to get rid of the trig are the Pythagorean properties. And to have the Pythagorean or to use the Pythagorean, we need it to be squared. So we need to square both sides. We need to square both sides. Now, for cosine and sine specifically, the next direction would be like elimination of equations or using solving systems with elimination, where you can add or subtract 2 equations or even multiply the certain constants and put them together. I would say add both equations, but it changes based on the trig that you have. So in general, square both sides and then look to, I'll say in general, the Pythagorean properties to the Pythagorean properties, and somehow you want to add or subtract the equations, then technically the direction would be simplified. Guys, the directions are longer on this side just because they're new. On the other side, we've kind of done the whole, like, take the x, solve the beta, plug into the y. But the math was hard because once we actually solve for x, there's this whole inverse cosine thing going on. And so when we plugged in, we're like, I don't know what to do with that. Like, it's a thing, but how do we figure it out? We have to use this triangle. On the left, let's see if you think it turns out any nicer. So let's follow the steps. Step number 1. Solve for trig. Number 1, solve for a trig. So number 1, we're going to go ahead and try to get cosine and sine alone. So I'm going to divide x by 2 to get cosine alone. I'm going to divide y by 3 to get sine alone. Looking at my original equation, divide both sides by 2, divide both sides by 3, getting cosine alone and sine alone, getting my trig alone. Step number 2, square both sides of what? Of everything. I could do cosine squared like that, but try to let you guys still see the steps. We're not used to seeing cosine squared like that. We're used to seeing cosine squared like this, but then it's trig notation. Don't get tricked by the trig notation. Do the same thing with the bottom equation. Square everybody. Okay, sine is squared. Y over 3 is now squared. Now, this is where it gets a little tricky if you've been able to follow me so far. Look to the Pythagorean properties. I don't get it. Wait, do you guys see a cosine squared and a sine squared? Oh, if only we had cosine squared plus sine squared. Because what would that equal? Plus. Okay, well, add or subtract the equations. Well, the Pythagorean property says plus. So I'm going to add the two equations. On the left-hand side, add what you got. It is what it is. X over 2 quantity squared plus y over 3 quantity squared equals cosine squared theta by sine squared. Okay. The point was to get rid of theta. And guys, Pythagorean property says, what can I now do? He's gone. 1 remains. Cosine squared, sine squared is 1. Over here, I can simplify. I get x squared over 4 plus y squared over 9. And some of you are like, hey, isn't that a conic section?
Oh my.
Isn't that an ellipse? Because it's addition with an x squared and a y squared? Wait a minute. Whoa, whoa, whoa. Maybe you're thinking you just said these are the same thing. Doesn't look like it. Question, isn't one side solved for y by itself? Isn't the other side not? Now the tricky one, tricky, maybe it's both. The tricky one came out in the nice form that we're used to where we could figure out if we wanted to the minor radius by, it's a smaller one, square root of 4. The major radius by is the other one, square root of 9 is 3. And we could graph this one and say, okay, from the center 0, 0, over 2, horizontally each way, up 3, vertically each way, and draw our ellipse. This one, if we graphed it in our graphing calculator, it would look the same way. So, it wouldn't have a plus or minus, that's the first. Maybe that's something that in my simplification of the process, I forgot to mention that we don't know what quadrant this is in, so technically we could put that in. But if we were to go ahead and try to get this one to look the same, the question is, would it? And the answer would be, let me just do it in gray, so that's kind of like a little extra step. What would this look like? Let's see. We would multiply up the 2 on the other side with the y, so we'd have 2y equals 3 plus or minus square root of 4 minus x squared. There's a yucky square root, so I'll just square everybody. I'll then get 4y squared is equal to 9 times 4 minus x squared. I could divide this side by 9 to get rid of that 9. I could add the x squared, which would get me to x squared plus 4/9 y squared. Just divide everybody by 4, which you might not like dividing by 4. Maybe it's easier to think about multiplying by 1/4, which would get you x squared over 4 plus 1/4. 4 is canceled. Y squared over 9 equals 1. Are they the same thing? And the answer is yeah. Yeah. It's a little intense. So, long story short, trig. It's a little different. I mean, it doesn't have to be. But if it isn't a little different, the math gets a little maybe beyond us. But if we want to use our trig, maybe the math is kind of more in line with what we're used to. So if you want to push yourself, maybe go for the right side. If you want to kind of just stay in line with probably what I would normally suggest Precalc students do, I would stay with, I'm just going to put it over here, the left side. It's a little bit easier. It has a little bit less new math in it. And it does get you where you want to go in the sense of, hey, there's no list. So to help you guys with that, I think I have a little slide. Let me quickly insert a page. Import below, just for sake of homework. But I don't want to import a document, I want to add a page. Got it. Let's just do a little comment section, you think? I'm just going to do a note. So note. Trig. Trig in parametric equations almost always means conic sections. Trig in parametric equations almost always means conic sections. And to help you to that end, let me go ahead and just do a quick example. If I have x equals h plus a cosine theta and y equals k plus b sine theta. One more time, it could be a t. If they're nice, they give you thetas because your brain is used to trading thetas going together. But let me show you without going through all the eliminating the parameter steps of what we basically just did. Long story short, you are going to end up with x minus h over a squared plus y minus k over b squared equals 1, which is, as we're used to, oops, I don't know what I was spelling, it wasn't the lips. Close.
Sorry. He's not even usually the catalyst. Wow.
Yeah, he might be a little. That didn't help. Just give that a nice friendly pat in the back. That's not a pat in the back. It's a weird white across the floor.
Ricky, that did nothing to
He's there.
Oh,
He's
there
fine. He's giving you his voice. Which you somewhat. Guys, I could keep going. There are conic section formulas with like secants and tangents and all kinds of craziness. But once again, we're not mastering parametric equations. We're not mastering them. We're just getting an introduction. Just realizing they're there. They show up in physics. They show up in calculus. Usually higher levels of calculus, like calculus 2 or 3, which isn't necessarily higher math. It's just deeper connections and applications and stuff. Parametric is especially though useful in physics and in modeling real world motion. But anyway, so this is an ellipse. I think you guys are going to see this in homework, and I just want to let you know how H and K and A and B kind of show up. One more big topic, which remember I said the last thing was the easiest thing in section 10.6. The last thing was the easiest thing in 10.6. So let's play with our calculators a little bit for 10.7, just get the title written down basically. and play with a new mode and just kind of figure out a few things so that tomorrow we might not, or we won't hopefully get as stuck as we might be other weeks. At the very end, finding the parametric equations. This is going the other direction, what we did so far in eliminating the parameter. It's like, okay, we have a parameter, so we have parametric equations. We're trying to get to what we're used to, so the rectangular ones, y's are functions of x's, all that jazz. Now we're going the other way. We have what we're used to. We need to get the parametric. Now, here's a long story short. To get the parametric, they have to tell you something about the time or something about the data. It's not there to begin with. It's gone. They have to tell you something about the timing. It's not that you're making up the timing. It's not at this level. They have to tell you about the timing so that you can plug it in and incorporate it. They have to tell you about the timing. So, here's the deal. Down below, let me highlight real quick. They give you a function that we're fairly used to. The parabola shift that one going down. It's actually the same one that we had that was all complicated in the example before. Or I guess two before. Not a tricky one, but the one before that. With the denominators and the fractions, the square roots, and all that jazz. So if we have a function, y is in terms of x, and then they all of a sudden, now these are two separate clues. You can't use both of these at the same time because the timings are different. So you can't make one pair of equations from different timings. You need one set way of understanding the time. So these are two different pairs of parametrics. Start with just A. If t is equal to x, that's our clue. Then what can we say? If t is equal to x, then, okay, here's the goal. We want to figure out what is x of t, or if you want, like your calculator puts it, instead of putting x of t, it puts a little x with a sub t. It is what it is, it's okay. Same thing as function notation. And y of t. If we're trying to get parametric equations, we're trying to plug in or find the pair. We're trying to find both what x equals and what y equals. If t equals x, then what does x equal? Hey, they told us. Just read it backwards. If t equals x, then x equals, okay, cool. It equals t. Well, wait a minute. If x equals t, then where else is x? In the y equals 1 minus x squared equation. So can't I just say, well, if x equals t, then can't I just plug in t? That's a good thing.
Are they all that easy?
Well, these are going to be just a little bit harder. They're not bad. They're not bad. Because in B, totally separate parametric equations, related, yes, because they both have the same path, but different timings. B, it says, okay, fine. If we change this up a little bit. So, Ricky, technically it's only going to get complicated if the t expression gets complicated. If t equals 1 minus x, then, once again, we're trying to find a pair of equations, x of t equals and y of t equals. I'm just writing it in the calculator mode because that's mostly where we're going to be doing parametric. Well, okay. What does x equal in this one? Gotta solve for it. It's okay to take a second and say, okay, I need to solve for x. So I'm going to subtract 1 from both sides. So minus 1, minus 1. Okay. Then I need to divide both sides by a negative or multiply both sides by a negative 1 because I need to get a positive x alone. And then if you guys want to, we're not used to seeing x on this side. We're used to seeing x on that side. Equations, if a equals b, then b equals a. We can switch them. So a negative x times a negative x will be a positive x. If we distribute our little negatives, we have a negative t and a positive 1 to make it look prettier. We can just say, oh, hey, there you go. So x equals 1 minus t. And how do we get the y equation again? Ding, 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 look at the side. Y equals 1 minus x squared. So you have x, so what are you going to do with it? Plug it in, plug it in. Yeah. Substitution, that's 4 now. Now if you want to make it pretty and stuff, and simplify, I suppose you can. It's up to you. It's not super important in the sense that we're just trying to get, there we go. Our expression to look good. We're going to distribute the negative. The ones are going to cancel. So we would have eventually 2t minus t squared. In which case, that just looks messy now, so we can go ahead and say x of t equals 1 minus t. So in the back of the book, I bet they give you the simplified form. Maybe they give you the non-simplified form. But, there we go. So, long story short, if you're trying to go from rectangular to parametric, they have to give you some sort of clue about t. And from that clue about t, basically, you just work your way backwards. Solve for x, that's your first equation. Plug in for x, that's your second equation. All right, guys. We already done our calculators. Go ahead and grab it out, and I want you to change the mode to polar mode. But if you guys want, that's your homework. Did anybody write down 10-6 homework? You can check it real fast. It'll be way faster than me going on there. Does it look good? The problem number is a little different. I think, oh, is it 65? Actually, maybe that's on track. Is that good? We'll say yes. So if you want to write down the homework, I think I actually did update it from your web sheet or your web assignment. All right, calculator's open. Vote, change it to poll. You might be writing down your homework. That's okay. I'm going to freeze the screen real quickly so I get my calculator all ready to go. I just want to show you a few funny things about polar mode. Parametric is cool and all because it only, it can graph not in, function mode graphs an infinite graph, or it doesn't actually, it does stop, has a beginning and end based on your window. It shows forever this way, forever that way. Parametric can cut it and say, oh, it's only going from here to here, it's going in this direction for these times. Polar, though, to be honest, is a lot more interesting as to how it graphs and what it graphs. We're going to learn a lot more about it tomorrow. I want you guys, first of all, to change your mode to polar mode. I'm going to go ahead and see if I can make this full screen. Okay. All right. So you're in polar mode. You're in that third setting of this line, which has function and parametric and sequence. If you know we're in polar, P-O-L-A-R, like the polarized cats. If we go to y equals, help me out real quick, kiddos. Let's just do clear, clear, clear. I'm not having you change any of the crazy settings unless you want to change, I don't know, I just had it bold because I think in BC we were graphing 3 different things at one point in the last couple of weeks. Let's see if we can circle, that's okay. Alright, let's start with something basic, let's do let's make it a little bit fun. How about sine of 4 theta? No, let's make it something even bigger. Let's do 5. Okay. Ironically, it's way different. Okay. Now, I don't want you to touch any zooms. I don't want to touch any of the windows. I just want you to go straight to your graph, whatever random setting you have it on, whether radians or degrees or what. I just want you to hit graph. Let's see if we all get the exact same picture. I'm going over and over and over and over again. It's going to keep on going over and over and over again. I'm going to go change something real fast. I know I told you guys not to change anything. Just because that's going to keep on going forever.
That's fun.
Let's go to 2.
Let's stop.
Okay. And then I'm going to zoom in. See if it goes faster.
What's the star? Really cool drawn star.
It is a poorly drawn star. It's just a little rough. You could try to zoom square and see if that makes it any prettier, which is number 5. I'm not going to make a big difference though. Okay, how many of you guys got a star? Of some sort. Or it's actually called a 5-petaled rose. How many of you guys got nothing at all? Okay. How many of you guys got something that's way different? Let me show you a few things real quick. I am in radian mode. So a lot of you guys that might have been in degree mode, it might have done something really weird. A lot of you guys that are in degree mode might have done something really weird.
That's weird.
Let me show you how weird it can get. Okay? If I was to go to my window, and if I was to change, theta min, theta max, I think we kind of had that with T's, right? If I was to change this to something like 50, and make it way bigger than radians, 2 pi, maybe that has a correlation. Degrees, maybe you should have done 360 or 720, maybe that would have made a difference. What if I was like, okay, hold on, let me inform you real quick. Theta step, remember T steps? T steps were like what steps to take as far as what times to graph. Theta step is saying what angles to graph. Kiddos, how many point 2s are there in between 0 and 50? A lot. So, if I wanted to graph by like really slowly, I would keep the point 2. If I want to go from 0 to 50, alright, fine. Point 2 is going to be accurate because if you think about radians, the number ranges are way small. Degrees, the number ranges are way big. Well, let's say I understood theta steps. It's how many points it's going to graph. Every point 2 is going to graph point 1. So I'm going to speed it up. Don't make it 5. Just a quick heads up. I'm totally distorting this thing. I'm going to get something a whole lot crazier. And it's going to look way different than it's supposed to. And the reason is, I can have it even be a lot more fun. I can have it go to something like, I don't know, 100. Or even 1,000. It'll keep on going and having a lot more fun. But the long story short is that this is not at all what this graph is supposed to look like. It's supposed to look like a 5-petal, like daisy basically, even though the mathematicians call it rose. They have some issues with that. But it's not graphing what it's supposed to. I can even show you something else that's going to be way distorted. And if I was to make it a theta and delete all the rest. This is going to really distort it too, because you can't even see it. Here's the long story short though. If I was to go back to our original one that I had, and if you guys were in degree mode, how we would make that one appropriate with our sine of 5 theta in degree mode, if I was to change it. You guys saw what I was in radians. If you wanted to see the picture in degree mode, you would go from 0 to maybe 360, maybe even 720. And if you went from 0 to 360, going by 5s is going to get you a lot of points in between 0 and 360. And since you're in degrees, it's going to look a whole lot better, and you're going to get the same flower that the rest of us got. But in degree mode, if you were instead to say, hold on, touch. If you were to go to point 2, like if you were to do that radian thing, guess what? Oh, that's not the right one. No, it's not that it's not going to show anything. But how long is it going to take?
Forever.
So at least you have an idea of theta min, theta max, theta step for tomorrow before we start. I guess.
See you, Mr.
Have a great day, Mr.
Okay.